Hey, so one thing that's, well, a couple things to start off before content. The 9th problem set is due on Wednesday. It's all about climate control, basically, in a house, or well, in a cabaret. So it's the material from Chapter 8, Thermodynamics. And the last problem set I'll put up after that one's due will be on clocks, which is the main topic for today. Any questions about that stuff? The problem set? Just to remind you, I dropped your lowest problem set if you complete the course evaluation for the class. And they did send me an email saying when it would show up, and I don't remember exact numbers, but I believe it's November 30th, and it runs until like December 7th. I'll try to remind you when it actually shows up. And nudge you once to try to complete it. Anyway, so I drop your lowest problem set if you do that, of the 10. Anything else? The other thing is, there will not be class on Friday. Big hardship, I know. Complicated story, but I can't do it on Friday. All right, and the other thing, well, related to this is that we'll actually get through the material this semester, which it's been a while since I got through everything I wanted to get through. So I'm kind of happy with that. Okay, so where we left off last time, and just to sort of remind you, actually a fair number of you came, on Monday last week, talking about automobiles. I just wanted to say 2 cents about a few items left over from automobiles. I hope you have a sense for, okay, first of all, the big picture issue is that automobile, I focus primarily on the engine. We can do all of physics in the automobile, but I just like enough is enough. The engine is the issue for thermodynamics. And it's a heat engine, and that is, it extracts some of the heat flowing from a hot object to a cold object and converts that heat into a usable work, into the equivalent of work, ordered energy. It does that, it can do that despite the law of entropy because it is creating entropy by letting heat flow from hot to cold. That flow from hot to cold creates entropy, disorders the world, and rather than take the full disordering that you would get simply by burning gasoline in a bonfire, it creatively extracts some of the heat flowing from hot to cold and turns it into mechanical energy. Work drives the car. The limitations on that imposed by the law of entropy are that finally you can't convert all of the heat flowing from hot to cold into work. You can only convert a fraction of it, and the fraction increases as the temperature difference between the two, the hot and the cold become bigger. So it is to everyone's advantage to have a hotter hot and a colder cold. So that's the big picture view of automobile engines, heat engines. You okay with that? Any questions about heat engines in general? They're all over the place. They power the weather too, but that's the natural heat engines of the world. A thing I left out last time that I sort of wanted to touch before leaving is the difference between an internal combustion engine, which is equivalent to a gasoline engine, and a diesel engine. Diesel engine is also an internal combustion engine. It's just for some reason they're just distinct names. And the difference is this. The internal combustion engine, gasoline engine, uses a spark plug to light the fuel and air. So it mixes the fuel and air right at the beginning of the force strokes, during the induction stroke, when it's sucking air into the piston cylinder pocket. It injects fuel right there, right then. And what it compresses in the next stroke to high pressure, density, and temperature is a mixture of fuel and air, which is itself flammable. And that is a problem because if you overcompress the fuel-air mixture or other things go bad, it ignites on its own, so-called knocking or pre-ignition, something that you don't want to have happen in your engine, at least not very often. And the way to avoid this, apart from tuning the engine better, is to go to the premium gasoline, the fancier gasoline, the higher octane gasoline are just harder to light. They tolerate more this compression, the temperature surge associated with compression. And just to remind you that when you compress a gas, you inevitably raise its temperature because you do work on it. And the work shows up in the gas as thermal energy. It gets hot. So gasoline engines are limited in how aggressively they can compress the fuel and air mixture because it will ignite if they overcompress it. And okay, the first order solution is to buy fancier gasoline, pay more for it. Again, public service announcement, don't buy fancier gas than your car needs. If it runs right on regular without knocking significantly, go with regular, save yourself the money. The premium doesn't buy you anything else except protection against pre-ignition, which you're not having anyway, so who cares? High compression engines, there are some that go to higher temperatures, they compress harder, and they go to higher temperatures, they do need premium gasoline. Fine, if you can afford those engines, you can afford the gasoline too. All right? A diesel engine, so that brings me to the diesel engine. So the diesel engine, essentially faced with this problem of the fuel and air mixture igniting before you fire the spark plug, before it's the right time in a gasoline engine when you overcompress it. The diesel engine goes, well, you know, what if you compress air instead of compressing fuel and air? Leave the fuel out. Just compress air. And that's what a diesel engine does, is it sucks in air during its induction stroke, no fuel, just air. It compresses the bejeebers out of that air during the compression stroke, so the temperature goes very high, and then it injects the fuel. So it has no spark plug. It doesn't need a spark plug. The high temperature necessary for ignition is already there in the compressed air. And it shoots the fuel in under extremely high pressure, 20, 30,000 pounds per square inch. So that's way over 1,000 atmospheric pressures. It's way beyond the pressure you find in a scuba tank or in a gas storage cylinder. So it's really high pressure. They fire the fuel in with a pulsed valve, and it bursts into flames because it's being shot into really hot air at like 5,000, well, at least several thousand degrees on some scale, really hot. It bursts into flames and it burns very fast. And then they go into the power stroke, just like in an internal combustion engine. So the key difference is the diesel engine doesn't put the fuel in first. It just compresses pure air, which obviously can't burst into flames, even if you get it very hot. And then they inject the fuel, which then does burst into flames. So the primary difference between gasoline and diesel fuel, apart from the most important physics issue, is that gasoline is hard to ignite deliberately, because if it was easy to ignite, you would never manage to compress it in the fuel and air mixture. So it's hard to ignite, and the harder it is to ignite, the fancier the gas is, the more you pay for it. So premium gas is especially hard to ignite. That's gasoline. Diesel fuel is easy to ignite. It's selected and designed, engineered to burst into flames instantly when it goes into that hot air. So they're sort of the opposite ends of the spectrum, which is why you don't want to swap the two fuels. I'm still not quite sure why you can't put gasoline in a diesel engine, but certainly if you put diesel fuel in a gasoline engine, it's the wrong stuff by far. It's too easy to ignite. Oh, nothing good will happen. You okay with that distinction? Okay. With that, I'll leave cars, I think. There are other things, you can go on endlessly. And I'll go into something completely different, which is clocks. All right? And the story of clocks, so why clocks? It's because we somehow became fascinated with being able to divide up time into well-defined intervals. So we knew when it was breakfast time or lunch. Okay. I have incidentally just filmed the lecture video for this. I'm sorry I run so tight. It's not very helpful, but it is what it is. So it'll be up after class. Great. You can get anyway. Okay. So the story of clocks then is about how you divide up time, how people figured out how to divide up time, and the devices that do this for us. And as you can imagine, things started way back with non-repetitive motions as timekeepers. So things like burning a candle. I could be giving out your midterm exam runs for one candle. You light it at the beginning. When it's out, you're done. All those non-repetitive things, water clocks, hourglasses, candles, and such, were okay for measuring sort of an interval of time. And if you had a whole box full of candles, you could, in principle, have multiple intervals of time. But when clocks really became interesting was when they could automatically break up time into well-defined intervals and actually count the intervals and tell you how many have gone by. And it might well be counting intervals that are 1 second intervals. And if it counts to 60 of them, it's a minute's passed. If it counts to 3,600, an hour's passed. If it counts to 86,400, it's a day's passed. So clocks are all about getting a well-defined interval that's sort of ticked off by a device that I will call a timekeeper. So it's some ticking device that rhythmically picks off intervals, and a counting mechanism for those intervals, and something that keeps the ticking going, which ultimately is an energy source, because the ticking motion involves energy. It's physics we've seen before. It's going to be bouncing motions, as we'll see in a minute. The bouncing motion that we've hit repeatedly this semester is all about going back and forth around equilibrium. It's about a battle between restoring force trying to put you back at equilibrium and inertia making it difficult to sort of turn around and come back to equilibrium and stop there. Inertia just keeps you moving steadily. So we'll see that the timekeepers that matter in clocks are all involve a battle between a restoring force trying to get you to the equilibrium and inertia trying to keep you doing what you're doing. And you is the timekeeper. And the system being unable to settle at equilibrium as long as it has excess energy. Again, a story that you've seen a zillion times already this semester. Excess energy keeps things going. And therefore, clocks, it turns out, will involve excess energy. And because they tend to waste it eventually, and therefore be prone to settling at equilibrium, you have to have an energy source that keeps the motion going so it doesn't settle at equilibrium. You don't want equilibrium as the destination anymore, because in a clock you want the motion to continue forever. Okay, so that's sort of the big picture view of clocks. A timekeeper, an energy source that keeps the timekeeper going, and a counting mechanism that counts the cycles of the timekeeper, the ticks. All right, so clocks move from the world of one-off things, burning a candle, to these cyclic things that keep ticking off time. To be accurate, though, that timekeeper has got to be pretty insensitive to problems, to influences from the outside world, temperature, weather, air pressure, all the things that can cause trouble. And it's got to be as insensitive to its own movements as possible. And as we'll see, what I have in mind is things that go through rhythmic motions around an equilibrium or about an equilibrium. They can make big motions or little motions. So I'll just preview this. So this is a rhythmic system. It's called a pendulum. It's an object on a support. In this case, it's a little cable or string. It could be a rod. It's something that connects this object here, which is called the pendulum bob. I didn't know why Bob got it as opposed to any other Fred, Joe. It's a pendulum bob, and there's a pivot at the top and something that keeps the pendulum bob at a well-defined distance from the pivot, but allows the bob to go about the equilibrium. So the equilibrium's here, and this is where it would settle to if there were no excess energy. But if you give it excess energy, and the clock does, it will keep moving about equilibrium. It never settles at equilibrium. It does the usual thing I've walked us through 100 times of it tries to go to equilibrium, but when it gets there, it's moving, so it coasts through. It overshoots, it comes back, it overshoots again, back and forth, and until it runs out of energy, it's going to keep doing this. And what drew me over to show you this right now is there's another feature of systems that go around a stable equilibrium that we got to pay attention to, and that is what's known as the amplitude of the motion. First off, I'm going to call this an oscillator just because it's a generic term that shows up in physics and engineering for something that goes rhythmically through a cycle. An oscillator undergoes an oscillation. What's the difference between an oscillation and a vibration? Not very much. They're just, maybe in the context matters a little bit. But so it's oscillating. I wouldn't call this vibrating about the center. It's just it sounds wrong to my ears. But anyway, it doesn't matter what you call it. It's this rhythmic motion. And it's got some characteristics that matter. The most important one for a clock is a characteristic known as its period. And what the period of something doing this, an oscillator, is the time between a starting point, pick one, like now, and how long it takes to return to the equivalent point again, now. So this has got a period of about, last I measured, it was like 4.5 seconds. It's from, here's a starting point, now, and it's back there exactly. And the starting point involves both position and velocity or momentum. I wouldn't say, it's not from now to now because the momentum reversed. That's not the full cycle. So you pick a point. If you pick a point which is equilibrium, you've got to watch both travels around the equilibrium. So it's kind of messy. So I picked in. Anyway, that's period. The period of the motion is how long it takes to go through a full cycle. You okay with that? The other characteristic that's worth paying attention to is the size of the oscillation. Size measured how? Well, it's often measured in space. In this case, we can measure it as a distance from one end of its swing to its other. That's the size of the oscillation. And we can say that's the amplitude of the oscillation. The word that comes up here is amplitude. And whether it's the amplitude from one extreme to the other, or whether it's from equilibrium to one extreme, doesn't make much difference in this context. The definitions ultimately, the details matter, and you're doing calculations, but we're not doing calculations. So this oscillation has a period, and it has an amplitude of oscillation. That about does it. And the feature that we're going to want for a clock is this. You want the period of the oscillation, the tick rate, to not depend on the amplitude of the oscillation. Why? Because it's hard to control how far the thing swings. And it wastes energy, and so the swing gets smaller. The amplitude gets smaller. And you try to fix that by giving this thing rhythmic pushes. Remember, you can put energy in either with one big wallop, or you can put it in rhythmically by doing work on it a little bit at a time. A little work, right? You can do it like that. Whenever I'm doing the work or not doing the work, I'm mucking around with the amplitude. And a clock that has a period, that has the timekeeper. I forget now whether I used the word timekeeper yet. This could be the timekeeper for a clock, the ticker. And if the timekeeper of the clock depends on if its period depends on its amplitude of motion, that is how big the motion is, little or big or in between, the clock's just not likely to be very accurate. It's going to be messy. While I was playing around filming the lecture video, it occurred to me, let me show you let me show you this first, and then I'll go back to that. This has everything you need for an oscillator. It's got a stable equilibrium. You're looking at it. This is back in the days of tricycles, right? And if I take it away from equilibrium, like this, it will oscillate back and forth about equilibrium. Oops, this one doesn't do it as well as the one downstairs. Man, my one downstairs went back and forth about 5 times. It was really nice. And do I have anything like that? No, but I can give you another. I got another. I will animate this one to show you what it looked like, and then I'll do a different. This guy, when it's really big amplitude, it takes a long time to go back and forth, and then it goes faster and faster, and it settles, right? And you've seen things do this before. Here's another thing that does that. The tick of this guy, tick, 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 tick. The smaller the amplitude of the motion, the faster it goes, the shorter the period becomes. It's a lousy thing to base your clock on. If you want to tick off the time with this, you can do it if you're a really good basketball player. And you can always hit it just the same height every time. But otherwise, it's going to be ticking at wacky intervals. The same with my rocking this guy. An oscillator that has the characteristic that its period depends on its amplitude of motion, like these guys do. It's technically known as an anharmonic oscillator, and it would make a rotten clock, rotten timekeeper for a clock. Okay? Anharmonic, where'd that word come from? You know, there are reasons for it existing. So clocks are built not using anharmonic oscillators, but harmonic oscillators. And a pendulum is almost a perfect harmonic oscillator. Let me show you how a pendulum behaves, and then I'm going to show you the generic, prototypical harmonic oscillator and explain why it's a harmonic oscillator, define harmonic oscillator. And I hope at this point you're starting to see why having a harmonic oscillator why an amplitude-independent oscillator, one that has a period that doesn't depend on the amplitude, is good for clocks. And it will turn out harmonic oscillators fit this bill. So this guy is, I'll claim it's a harmonic oscillator, which I haven't defined yet, and I'll come back to in a minute. But the symptom of being a harmonic oscillator, so if you look at the rules and say, oh, you know, this thing fits the rules for harmonic oscillator, it is one. Here's what you get. A harmonic oscillator has this cool feature that its period of motion doesn't depend on its amplitude of motion. So that means, and this I claim is a harmonic oscillator to very good approximation. It's not perfect for interesting reasons, but it's very close. And the result is this, that if I swing it only a little bit, start, stop, that period, which I think is 4.5, every year I muck around with this, we measure it. And to measure it decently, you have to measure a couple periods. So I think it's 4.5 seconds, and we'll see why it's 4.5 seconds in a minute. That's the period of it when it's swinging like this. How about when it's swinging like this? Tick, tick. It's the same. So this motion, which is much bigger and involves larger velocities, more momentum, bigger accelerations, all that stuff, this thing still manages to go through its motion just as it did when it was swinging a little bit. It doesn't matter. This motion involves smaller accelerations, smaller velocities, it works, but the period comes out the same anyway. Any questions about this as a notion? Well, let me give you some background on why. So why does that work out? And what is a harmonic oscillator? Well, I'll give you essentially the definition of a harmonic oscillator. A harmonic oscillator is an oscillating system which intrinsically builds in the notion that it's working its way around a stable equilibrium. It's an oscillating system so it has an equilibrium. When you pull the moving part, I don't know what to call that, the oscillator, when you pull it away from equilibrium, displace it from equilibrium, a restoring force shows up, and that restoring force is proportional to the displacement from equilibrium. So the pushback, when you pull the thing away, whatever it is, away from equilibrium, the pushback is proportional to how far it is from equilibrium. It should bring to mind the idea of a spring. A spring has this characteristic that if you take the spring at its equilibrium shape and you pull it away from equilibrium shape, it develops a restoring force on its ends that is proportional to how far you've pulled it away from equilibrium, from its equilibrium shape. That was Hooke's law. That was back in spring scales. Is that familiar? I hope. So lots of things in the world fulfill that requirement. This guy, for example, remember springboards? A springboard has the characteristic that it's got an equilibrium shape. You know, gravity is involved in this, but gravity, as we'll see in a second, or I'll try to tell you in a second, just doesn't play an important role. If I pull it away from equilibrium, 1 centimeter, it develops 1 unit of restoring force. 2 centimeters, 2 units of restoring force. Go the other way, you get 2 units of restoring force the other way. It all works out. That fulfills the requirement that I'm just describing for a harmonic oscillator. So let me make sure I actually said the whole thing. A harmonic oscillator is an oscillator that has a restoring force that is proportional to the displacement from equilibrium. Questions about that? So what do you get if you fulfill the requirement of a harmonic oscillator? You get this cool effect that the period of the oscillation doesn't depend on the amplitude of the oscillation. So the prototypical harmonic oscillator is a mass on a spring. Why a spring? Because it's got Hooke's law. It's got this characteristic that its restoring force is proportional to how far you take it from equilibrium. Why the mass? Because the mass is the prototypical oscillator. It's the thing that will go through its motion. And anything that fits the bill of being the oscillator, the going through motion, has inertia. So this is harmonic oscillator is always about a battle between inertia trying to keep things doing what they were doing and the restoring force saying, no, come back to equilibrium, come back to center. And so this bouncing motion, which we hit back in the days of spring scales, this motion is the motion of a harmonic oscillator. It's a harmonic oscillator because it's got a spring as the restoring force. Perfect. It's exactly what the doctor ordered. So it's got a restoring force that's proportional to displacement, and it's got this oscillating thing that exhibits the inertia that ultimately is essential to an oscillator. And this has a period that's independent of the amplitude of motion. It is a harmonic oscillator, so it for sure, it has that characteristic. So if I bounce it a little, let me do a little. Tick, 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 tick. Or I bounce it a lot, short of coming off. Tick, 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 tick. Same period. And what else about this? Regarding the battle between inertia and the restoring force, I hope, I've done these sort of animations. Let me do it one more time and hope you're all happy with it. I'll go slowly. When it's down here, it's stretched too far, the spring. The spring is pulling back hard. I should take a moment and say, gravity looks like it's important here, but it's not. If we turned off gravity, all that would happen was this would move up to here. That's the only difference. Now we would be bouncing up and down about this point, driven by the spring. Because we've got gravity, we bounce up and down about this point, driven by the spring. The spring is the only force-exerting thing in this story that cares about where the bob is, the bouncing object is. Gravity doesn't. Gravity's constant. So whether the bob is up here or down there, who cares? Gravity gives it the same downward force. So gravity doesn't drive this back and forth motion because it's not affected by where the thing is. It's indifferent. It's indifferent to the motion. It just says, I pull you down, steady. And that just shifts the equilibrium, and then gravity's out of the story. I hope that's vaguely acceptable if it's not believable. So this thing bounces up and down, and when I pull it down here, the spring is overstretched. The bob is pulled upward towards equilibrium, and it accelerates upward. So it picks up speed, it gets to equilibrium, which is right about here, and it's no longer accelerating, but it's coasting right through, and it overshoots. And it goes up here, and now it's accelerating downward, and it comes to a stop momentarily, and then it picks up speed, and it gets to equilibrium, and it coasts through. So the mass, and therefore the inertia of this guy, determines sort of how hard it is for the restoring force to get the bob's attention and pull it back, change its velocity to bring it back towards equilibrium. So the more mass you have here in this object, the slower that object is to turn around and come back each time. So increasing the mass will slow down the cycles and make the period longer in time. You okay with that idea? I can show you that effect. As I do this, it's going to shift the equilibrium position, which will be disconcerting but unimportant. So when I do this, where's the equilibrium going to be? All the way down there, okay? But the bounce, we can still bounce from out equilibrium. Bounce, bounce, bounce. It's like a 2-second period now, as opposed to bounce, 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 bounce. So the more mass you put into the oscillator, the more inertia you put in the oscillator, the longer the period gets. You okay with that? The spring is also involved in this story because the spring tells it the stiffness of the spring, how much it fights distortion away from its equilibrium. That determines how aggressively the system turns around and goes back towards equilibrium. So the stiffer the spring is, the faster the return of the object after going through equilibrium one way, the sooner it shows up coming the other way. So if I stiffen the spring, the period gets shorter. And I can show you that. Here again, the period. Tick, 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 tick. I've got a stiffer spring here. Tick, 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 tick. Okay? So, as I say, this is sort of the prototypical harmonic oscillator. A mass on a spring. The mass is literally the inertial part. And the spring is literally the spring-like restoring force that the harmonic oscillator needs. So if you get this arrangement, you get a period that's independent of amplitude. And I can do that too. This is oops. Yeah, that would be big bounce. There's limits. Okay, you get the idea. The period's independent of amplitude. Is that okay? All right. So to build a good clock, pick a harmonic oscillator. The first of the harmonic oscillators to be picked was the pendulum. So this guy, it has the inertial part is the object. It fulfills the requirements. It's the oscillator. It has inertia. It has a mass, in fact. It goes through its motion, and it's got a restoring force. And the restoring force is almost perfectly proportional to how far you take it from equilibrium, the displacement. As I pull this away, it's kind of like riding up a weird ramp. So it's on a string, but you can sort of think of it as riding a ramp. Here's the ramp. Right now the ramp is horizontal. It's on a sidewalk. But if I take it away, it's now on a ramp. And the ramp gets steeper and steeper as it goes higher up. And as a result, if you think about the ramp force when the ramp is horizontal, it's a sidewalk, there's no force. But as you go here and the ramp gets a little bit, there's a downhill force, but it's very gentle. And as you get steeper, the downhill ramp force gets stronger, bigger force. And long and short of it is the restoring force back towards equilibrium is almost exactly proportional to how far you take it away from equilibrium. It's almost a harmonic oscillator. Good enough, for all practical purposes, it's good enough. So this guy's got a period, because it's a harmonic oscillator, it's got a period that doesn't depend on amplitude. That's the 4.5 seconds. So what does it depend on? Well, depends on two things. In this respect, it's a little unusual for harmonic oscillator. First, let me remind you how the words prototypical and archetypal and stuff, I've never learned how to use properly. I've never been confident I know how to use them. Anyhow, so this is the classic. Maybe that'll do it. Koch classic. That's before your time, though. Anyway, it's the period of this classic harmonic oscillator is determined by the stiffness of the spring and the amount of mass in the bouncing, oscillating object. That's all, okay? And hopefully in intuitive directions. That is, the stiffer the spring, the shorter the period. The bigger the mass, the longer the period. The details of the numbers don't matter. So you can usually boil harmonic oscillators down to the stiffness of a spring-like thing and the amount of mass in the moving object. With one exception, the pendulum. Why? The pendulum is weird. The pendulum has a period that doesn't depend on the mass of the moving object. It's essentially the only such harmonic oscillator. If I add mass to this bowling ball or reduce it, it won't change the period. That's, hopefully that bothers you. If I change the mass of that bouncing cylinder there, it would definitely change the period. Not so here. Why not? It's because increasing the mass of this thing will definitely increase the inertia. And that will, normally that will make the whole motion slower and longer, bigger period. However, the restoring force in this unusual harmonic oscillator, the restoring force depends on gravity and the weight of this object. And the weight of this object depends on its mass. So if I increase the mass of this object, I accidentally also stiffen the restoring force. If I hang on this, wrecking ball, I've invited a guest star. Miley Cyrus will be here to play. Okay, if we add mass to this, that by itself will slow down the motion. However, it will also add weight to this guy. And that means that taking away from center will incur a bigger restoring force. So pendulum is a weird exception where the mass of the swinging object doesn't matter. Even though it's a harmonic oscillator, changing the mass, it's not going to change the period. It will, almost every other harmonic oscillator will, this one not, because the restoring force also depends on the mass. You okay with that idea? So what does a pendulum's period depend on? Two things. The length of the pendulum, which is officially, by physics, is the distance from the pivot to the center of mass of this object. So that's that distance. So it's to about, it's in here somewhere. I can't touch it. That length matters. That's one thing that matters. And how does it matter? The shorter I make that distance, the faster the thing swings. So for example, that thing, I don't know how many meters it is. It's long. This is a 1 meter pendulum. And instead of being 4.5 seconds, it's almost exactly 2 seconds. So tick, tick, tick. So this is suitable for a grandfather clock. This is a 1/4 meter pendulum. Oddly enough, shrinking the length by a factor of 4 reduces its period by a factor of 2. The period depends on the square root of the length. I can't help it. It is what it is. And so that's a 1 second period. Tick, tick, tick. It's a nice wall clock. So wall clocks usually use 1/4 meter pendula, grandfather clock, and they tick off seconds. Grandfather clocks usually use 1 meter pendula, and they tick off 2 seconds per tick. It's not exactly 1 meter, not exactly 1/4 meter. It depends on one other thing, because the length matters. The other thing that matters is the strength of gravity. The stronger gravity is, the stiffer that restoring force becomes. The more the pendulum fights being away from equilibrium, so the shorter the period gets. So if you take this pendulum to Jupiter, where the gravity is strong. It'll go back and forth several times faster. Take it to the moon, it's going to be doing very leisurely swings because gravity is so weak. Okay? So the period of a pendulum depends on the length of the pendulum and the strength of gravity, and nothing else. It does not depend on the mass of the bob. Hopefully you can sort of remember the way in which it depends. The longer the pendulum, the slower it gets, and the stronger the gravity, the faster it gets. Is that okay? The fact that a pendulum, so a grandfather clock, I'm sorry, a pendulum clock. So this is my office. I never had this for forever. This is a pendulum clock. There's the pendulum, and it does fulfill the bill of being a harmonic oscillator. It's got a swing period that doesn't depend on the amplitude of the swing. It is not a round pendulum bob anymore. It's a disc that's been sliced because it needs some aerodynamics. It wants to be streamlined. It does not want to be encountering pressure drag if it can avoid it. So in a properly designed clock, you don't use a ball. You use something that slices through the air nicely in a streamlined fashion to avoid pressure drag. So the swinging continues for a while, like this guy's going on. It will still eventually stop swinging. So how do you keep it going? An energy source. And the classic energy source for a pendulum clock is a heavy weight that rides on a chain. And I just packed it full of gravitational potential energy by doing work on it. The potential energy is there now. And as this pendulum swings back and forth, mechanisms inside the clock transfer little bits of energy from the descending weight to the swinging pendulum to keep the pendulum going. The mechanism is a cool thing called an escapement, and not worth doing the details, but it basically automatically gives little pushes to the pendulum once per swing, just like you would do work on the pendulum with your finger. So it keeps the pendulum going, and the rest of the clock does one simple thing. It counts the swings, and it counts them in a way that allows it to display minutes and hours. And if there were second hand, it could do seconds. But it's sort of ticking them off. And this pendulum has some weird, I've still never measured the period. It is longer than 1 second, but it is shorter than 2 seconds. And the gears are cut to take that into account and quantify time properly. And it keeps pretty good time. I mean, I have to adjust it. Every time I bring it up here, I muck it up. I change the length of the pendulum ever so slightly. And any decent pendulum clock has an adjustment on it. There's a little adjustment here at the bottom, a little piece of metal on a screw. And by moving that metal up and down the screw, I change the effective length of the pendulum from the pivot to the center of mass here. If I move the center of mass, which I do by knurling that knob, I change the period. And so I can adjust it to keep good time, accurate time. In general, a clock like this obviously is not very movable. I can't wear this on my wrist, right? Unless I want to walk around like this all day. So it has to be fixed in place. But additionally, it has to be adjusted for the local strength of gravity. Because if gravity here in Charlottesville is a little stronger than gravity up in the Blue Ridge. Up in the Blue Ridge, you're a little farther from the center of the Earth. Gravity is a little bit weaker. And as a result, this clock will run a little slower at the top of the Blue Ridge than down here, because the pendulum will go a little more slowly. The restoring force is a little weaker. So if you ever own a grandfather clock or a pendulum wall clock, you may well have to adjust it a little bit to be sure that it runs properly, depending on the local strength of gravity. Is that okay? All right. So that's the first of the harmonic oscillator clocks. I've tried to build the story for harmonic oscillators themselves. Okay. This is a harmonic oscillator-based clock. It happens to be this weird harmonic oscillator where if you change the mass of that pendulum bob, you don't change its period. But okay, that's worth stating and then forgetting about. How about if you want a clock that you can carry around or wear on your wrist? Well, if you're doing that, you don't want a clock like this with a restoring force that really depends on gravity. It has gravity in the story, which a pendulum does. And you also don't want a clock that has a weight bouncing on a normal linear spring. This, I claim, gravity is just a nuisance. It shifts the equilibrium down. But once that's happened, gravity no longer plays a role in determining the period of this oscillator. All that matters is the stiffness of the spring and how much mass you have there. Gravity, this will bounce at the same rate on the moon as on Jupiter, as in deep space. If you go to deep space where there's no gravity, woo, we're floating around, right? The mass will bounce around this equilibrium, the equilibrium it has when there's no weight, but it'll bounce about the same period. Okay? So this seems pretty movable or movable. You don't have to adjust for gravity. It's great. You can take it to the North Pole, to the equator, to the Blue Ridge, Charlottesville. You get the same period. However, because gravity affects the equilibrium position, ding, okay. Because gravity affects the equilibrium position, this is hard to work with as a timekeeper for a real clock, because as the gravity changes, the equilibrium moves up and down. As you tilt, it goes nuts. It goes sideways, whatever. Anyway, long and short of it is it's not very practical as a timekeeper for a clock you want to wear on your wrist. So what can you use as a clock you wear on your wrist? And the answer is, don't go into a mass on a spring in the linear. A question about the pendulum shrinking the length by a factor of 4 changes the period by a factor of 2. The square roots show up a lot in the motions and the characteristics of harmonic oscillators. They show up as a factor of 2 because changing masses and springs affects acceleration, which is related to position. Acceleration is the time rate of change of velocity, and velocity is the time rate of change of position. There are 2 steps in going from where you are to how big the acceleration is. And those 2 steps mean that ultimately lead to doubling something, either the mass or the stiffness of the spring. You have to share it between the step going from position to velocity and the step going from velocity to acceleration. You have to share it. So you only get a square root of 2. There's a factor of 2 in the mass, or a factor of 2 in the spring stiffness. But you have to share it into 2 parts, 2 steps. A square root of 2 and another square root of 2. And this is my hand-wavy way of saying that most of the time in harmonic oscillator land, in order to double the period or divide the period by 2, in order to change the period by a factor of 2, you have to change a characteristic of the oscillator by a factor of 4. 2 is the square root of 4, of course. All right? So in going from a pendulum that's 1 meter, where you get a 2-second period, to a pendulum that is more than 4 times as long as a 1 meter pendulum, you end up with a period of 4 and change seconds. All right? Let me just finish a little bit on the idea of a portable timekeeper. This is a mass on a spring, right? It's got some portability problems. This is a rotational mass on a torsional spring. It's the same concept, but in the world of rotation. And this is the rotational equilibrium. It wants to be oriented like that. This is a stiff metal wire that cares about whether you twist it. So if I take it away from its favorite orientation, it hates this. It fights. It wants to go back. So it experiences a restoring torque. And this guy oscillates back and forth about its equilibrium, but it's all rotational. I mean, if you set aside everything else aside, nothing else matters. These are identical, except this is linear, this is translation, this is rotation. And this rotational motion turns out to be very portable. You can take this, and the way I'll finish up here is I'll show you this. This is a carriage clock from the, well, now I'd say the previous century, but it's actually a century plus old. These clocks started showing up as a way to carry time with you, as pendulum clocks can't. And I think we can stare down at this from the document camera. Let's try this. Yeah. Okay, so we're staring down at the clock. And what I want you to see is at the top of the clock is a little wheel. See the little wheel there? That's the ring. That is that's essentially this guy. And the spring is a very fine coil spring that is very hard to see. In past years, I've managed to get it so it's vaguely visible. But right now, nothing's moving. If I wind this, I haven't wound it for ages. If I wind it, it'll have its energy source, but I have to get the little guy moving. And the way I've always gotten it moving is by giving it the whole clock a little shake. Okay, there we go. And the ring, it's hard, the camera doesn't run in like really fast frame rate. So, but hopefully you can see that the ring is actually rocking back and forth about its equilibrium, driven by the little coil spring. And the rest of the clock is a counting mechanism. Well, it's also an energy source and a counting mechanism for the ticking of that little harmonic oscillator. And with that, we'll stop and continue on Wednesday.